Hey everyone, Mr. Smith here with next unit's video notes. So we're starting Newton's laws of motion. In case you don't understand why we call them Newton's laws of motion, it's because Sir Isaac Newton is the one who created the three laws of motion. So the first and most important thing is defining force. A force is any push or pull on an object. And we know from previous units that forces cause an object to accelerate, right? Accelerate can be speeding up, slowing down, or changing direction. So Newton's first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an external unbalanced force. If you think for a second, unbalanced, if I push my hands against each other and I push with the same amount of force, my hands aren't going to move left or right, right? And we call that balanced, the same amount pushing from both sides. Now, if I push harder with one hand, so let's say this hand, than the other, eventually my hands are going to move. And that is what an unbalanced force is. We experience this all the time, right, in cars. When you're driving in a car, the reason that we have to wear a seatbelt is because of Newton's first law. Let's say your car is traveling at 60 miles per hour down the highway. Your body is also traveling at the same exact speed because we're in the car and we are like sitting in the seat, right? Now, if you get into a wreck and you run into the back of a car, your car stops because the force, an unbalanced force, stopped the car, right? But without a seatbelt, we have nothing that's acting upon us. And that's why you see these videos, if you've ever watched the movie Zombieland, right? And the person gets catapulted through the windshield and out of the front of the car. So our seatbelt is our external force, right? The car runs into another car. The seatbelt is what acts upon us, and that stops us from being launched out of the car. Another object, if you've ever been ice skating or watched a hockey game, is a hockey puck. If you've gone ice skating, you know that you can glide for quite a long time. Or if you've ever been lucky enough to get to play hockey, you can pass a puck from one end to the other without much effort. And that's because there's so little friction on the ice that we can see Newton's first law pretty clearly. An object in motion will stay in motion unless acted on by an outside force. And the force of friction is so small on ice that it almost seems like the puck could go on for forever. So one thing to consider here is our formula. Weight is equal to mass times gravity. Here on Earth, we'll say, oh, well, I weigh me 147 pounds, right? But what we know is that that is my mass that my body is made up of multiplied by gravity, 9.8. And we'll get our answer in newtons. I guess if you make up your own laws, you get to label the units whatever you want. And he named them after himself. Slightly narcissistic, but I guess I would do the same thing. So if we go to the moon, my mass, what's my body's made up of, does not change, but our force of gravity does. So my weight on the moon would be less than what it is on Earth. Now on to Newton's second law. Newton's second law is really famous for this formula. F equals m times a. Force is equal to mass times acceleration. We will do some calculations while going over this law, and this will be the formula that you use every single time. Here you can see what we call a free body diagram. And at the end of this video, I promise to go over and explain more in depth about free body diagrams. But you can see that this arrow represents a force pushing on an object. And so to determine how quickly the object accelerates, we also need to know the mass. An example here, let me get my pen, give me just a second. Okay, an example here is we have a frog from its resting position leaps on a lake's bank to a lily pad. I guess Miss Rivera wanted me to have a tongue twister while we're doing this. If the frog has a mass of 0.5 kilograms and the acceleration is 3 meters per second squared, it's asking for the force the frog exerts on the lake's bank while leaping. So we've written down our givens, we've identified our unknown, okay, and now it's time to write down our formula. F equals m times a. Substitute in, we've got m of 0.5, and we've got an a of 3. Now we solve. 0.5 times 3 is equal to 1.5. And remember, our units are newtons. So we would say that the frog exerts 1.5 newtons of force on the lake's bank. So I know that was a very simplistic version with small numbers, but the good news is with this formula, we have our triangle. If these help you out, we have a triangle of, let's find my pen, there we go, F, M, and A. So if you struggle on how to identify which formula to use, we can use this triangle. If we were given force and acceleration, we would have M equals F divided by A. You already know F equals M times A. And then lastly, you could have A is equal to F divided by M. So those are the 3 formulas. You'll see these on your formula chart, but just in case you're taking notes now, you can go ahead and write those down. So third law, this is one that makes a lot of sense in real life. For every action, there's an equal and opposite reaction. Or you can say for every force, there's an equal and opposite force. If I wanted to clap, I feel the force on both hands, right? Even though I'm applying force with this hand applies force back in an equal amount towards this hand, right? So there's a really famous question that will be on a quiz or a test somewhere, and it's going to say a bug is flying in the air and a car applies 50,000 newtons of force to the bug. Well, we know from Newton's third law that for every action there's equal and opposite reaction. So if a car applies 50,000 newtons to the bug is applying the same amount of force to the car. And that's why you see a big splat. Another example here is a rocket ship. We can see that the rocket ship is pushing the gas down, which causes the rocket to go up. There are lots of examples in real life about that, but those are some short ones. Here, we're discuss free body diagrams. So it says you rest an empty glass on the table. How many forces act upon the glass? Well, we know from real life that gravity pulls down on everything. So we're going to label this Fg for force of gravity. Okay, but none of us are being pulled through the floor or this glass through the table. So we also have what's called a normal force, Fn. Okay, this is the force that always opposes gravity. I'm sitting in this chair right now, right? And my chair is being pulled down by gravity, and I'm being pulled down by gravity. But luckily, I'm not ending up in the special ed office by being pulled through the floor. So remember from the beginning, we said that forces are either balanced or unbalanced. Okay, if I was going down through the floor, we would say that this is an unbalanced force, right? But since I'm not, we're going to say that our forces are balanced. Force of gravity is pushing down or pulling down, at the same amount that a normal force is pushing up. Okay, so how many forces? Well, we've got 2. We've identified them. We've also identified that these forces are equal because I'm not moving. Okay, and then are these forces in action and reaction pair? Well, if we didn't have the force of gravity, there would be no need for a normal force. Think about the moon, right? Or I mean in space, not necessarily the moon, but in space. Okay, I can float around because of the absence of gravity, so there's no need for a normal force. Now, I'll give you one more example of a free body diagram just to show you a couple of different things. Okay, I was out at my deer lease this weekend, so let's say that this is a bag of corn. I'll use that as an example. Now, I needed to pick up the bag of corn in order to pour it into the deer feeder. So what I needed to do is I needed to lift this bag of corn. Okay, we're going to call this force, and we're going to say that it was 15 newtons. Now, a couple of things. Gravity is pulling down on the bag, right? So we'll say that this is an F of G, force of gravity. Okay, now, because I was able to lift the bag before I set it on my shoulder, these forces are unbalanced. Unbalanced because I was able to move the bag up. Okay, but it was really windy. I don't know if anybody was outside. So I'm going to say that there was a force of wind. Okay, and we'll say that this was 5 newtons. Okay, force of wind that was pushing me and I almost fell over. Right, 5 newtons. But I was able to use my arm to push against a tree. Okay, so we'll say that this is a force of push, and it kept me standing upright. Okay, so we'll say that these forces pushing right and left are balanced because I was able to stay standing still upright. But these forces, force of me lifting and the force of gravity going down, are unbalanced because I was able to lift the bag of corn. Hopefully that this was a quick overview that gave you just an idea of some of the vocabulary that we'll be using. Each day, once we start this unit, we'll be going over a new law, Newton's law of motion, right, until we get through all 3 of them. So enjoy. Send us an email if you have any questions. If not, see you soon.